Salam, peace be upon you. Our story of change, part 18. What is probability? Where we are. Let us take a slow breath and remember where we are. We have been building something careful. We started with a cup. The cup was whole. Then the cup was broken. Everyone saw it happen. But we refused to say, time passed, so it changed. That felt too easy, too magical, too hard for strangers to check. Instead, we built folders called state packages. Each folder holds a snapshot of something at one moment. What we looked at, how we looked, what we are allowed to claim, how uncertain we honestly are, and a trail so anyone can repeat our looking. Then we built receipts called update certificates. These receipts prove that one folder legally leads to another folder. They pass through 8 gates, like 8 checkpoints. If a receipt fails a gate, we do not accept it. We write a refusal certificate instead and put it in a special drawer called the negative archive, so we remember what did not work. Then we built an immune system. If we discover an old receipt was wrong, we revoke it. And we revoke everything that depended on it. We call this a revocation dossier. Then we built a graph. Dots are folders. Lines are receipts. The whole drawing is called graph G sub U. We said, a universe is not a place. It is a connected record. Then we built order, not from clocks, from chains. We said, S1 comes before S2 if you can walk from the first folder to the second folder by stepping along receipt lines. Then we built propagation limits. We said, a change can only spread along paths that have legal receipts with open gates. No distance, no speed. Only connectivity and permission. Then we built transformers. We said, a law is not an equation on paper. A law is a registered machine that turns one folder into another. Every transformer lives in a public registry with its full declaration. Then we built composition. We said, we can put transformers together in a chain, but only if the types match and all gates still pass. Then we built conservation. We said, a quantity is conserved under a family of transformers if every valid receipt in that family shows it stays the same, within uncertainty. Then we built interaction. We said, two things interact when you cannot split the change into separate receipts for each thing. Interaction is certified non-factorization. Then we built equations. We said, equations are not assumed. They are what remains after all illegal updates are refused. Equations are survival conditions. Then we built branching. We said, multiple possible next steps appear when ceilings are low and uncertainty is high. The branch set is all the folders that could legally come next. Now we have many folders, many receipts, many transformers, many families, many patterns. And now, from some folders, many possible next steps. And that brings us to a new question. A question people have asked for centuries. When many things are possible, how do we talk about what is likely? The opening scene. The two paths in the forest. Imagine you are standing in a forest. The path splits in two. One path goes left toward the river. One path goes right toward the hill. You have never walked either path. You do not know where they lead. A friend who has walked both tells you, the left path is smooth and easy. Many people take it. The right path is rocky and hard. Almost no one takes it. Now you have information. Not just that both paths exist, but that one is more likely to be taken than the other. That is probability. It is a way of saying, among the possible branches, some happen more often than others. But here is the key. Probability is not magic. It is not a force. It is not written into the universe. Probability is a rule for distributing belief over legal branches under a declared scope. The big idea here is what we discover. Probability is not a primitive. It is not a basic law of nature. It is a certified assignment rule. Spoken slowly, probability is a typed measure over the branch set with normalization and invariance tests. No branch set, no probability. No scope, no measure. You cannot talk about probability until you have listed what is possible. And you cannot apply probability outside the scope where it was measured. What does that mean? Let us unpack it. First, we need a branch set. We need to know all the possible next folders from S, that is, B of S. Without that list, probability has nothing to attach to. Second, we need a scope. We need to say, under what conditions does this probability apply? Which transformer family? Which passport? Which domain? Which uncertainty? Third, we need an assignment rule, a way of giving numbers to each branch. The numbers must add up to 1. They must be the same for folders that are equivalent. They must not depend on forbidden things like observer choice or magic. Fourth, we need evidence. Why these numbers? What measurements support them? How do we know they are right? When all these are in place, we have a probability measure, not a guess, a certified assignment. The dice example. Imagine a die. You hold it in your hand. You have not thrown it yet. The branch set is 6 possibilities. 1, 2, 3, 4, 5, 6. Now, what is the probability of rolling a 3? In ordinary life, we say 1 in 6. But why? Because we assume the die is fair. We assume each side is equally likely. But that is an assumption. It is not given by the die itself. If the die is weighted, the probabilities change. If the die is shaped strangely, some numbers might be impossible. So probability is not in the die. It is in our knowledge about the die. It is a rule we assign based on evidence. The important turn. Now we say something that sounds strange at first, but becomes obvious. Probability is not a property of the world. It is a property of our certified ignorance. The world, whatever it is, does one thing. It rolls one number, but we, with our limited knowledge, cannot say which number. So we assign weights to the possibilities. Those weights are probability. If we knew everything, if we had perfect information, infinite ceilings, zero uncertainty, the branch set would shrink to 1. Probability would disappear. Probability exists because we do not know everything. The coin flip example. Imagine flipping a coin. The branch set is 2, heads or tails. Now, what is the probability of heads? If the coin is fair, we say 1/2. But how do we know it is fair? We flip it many times. We count. If it comes up heads about half the time, we say it is fair. That is calibration. We measure. We gather evidence. The probability comes from the evidence, not from nowhere. If we flip it 10 times and it comes up heads every time, we might suspect the coin is not fair. The probability might be different. So probability is not fixed. It depends on evidence. It can change as we learn more. The weather example. Imagine you wake up in the morning, you look outside. The sky is cloudy. What is the probability of rain today? You do not know from just looking. But you have experience. You know that on cloudy days like this, it rained about 30% of the time in the past. So you assign a probability of 0.3. That is a certified assignment. It comes from data. It comes from counting past cloudy days and how many brought rain. But it only applies here, under these conditions. If you are in a desert, the probability might be different. If it is a different season, the probability might be different. Scope matters, always. The probability measure interface. Now we build something new, the probability measure interface. For a given folder S, with a given branch set BS, under a given transformer family F, with a given passport PI, we can assign a probability measure P. P must satisfy 1. Normalization. The probabilities of all branches add up to 1. No more, no less. 2. Distinctness. Branches that are equivalent within uncertainty get the same probability. If two folders are the same for all practical purposes, they cannot have different probabilities. 3. Invariance. The probabilities do not change under allowed transformations. If we rename everything, phi goes to phi plus c, the probabilities stay the same. If they change, the measure is illegal. 4. Scope declaration. The probability only applies within the declared domain, under the declared transformer family with the declared passport. No scope, no probability. 5. Calibration provenance. The probability must come from evidence, from counting, from measurement, from repeatable observation, not from thin air. When all these hold, we register the probability measure. It becomes a public object. Anyone can check it. The calibration dossier. Now we add something important, the calibration dossier. This is a file that records why a probability measure is what it is. It says how many observations were made, under what conditions, what the counts were, what the uncertainty was, how we know the observations were valid, gate reports, how we handled outliers, when the calibration was done. This dossier is public. Anyone can check it. Anyone can try to replicate it. If new evidence comes in, the dossier can be updated. Probability is not forever. It is the best we know so far. The marble jar example. Imagine a jar of marbles. You cannot see inside. But you know there are red and blue marbles. You reach in and pull one out. You record its color. You put it back. You do this 100 times. You get 73 red, 27 blue. Now, what is the probability of pulling a red marble on the next draw? Based on this evidence, you assign 0.73. That is a certified probability. It comes from counting. It has a calibration dossier. It applies under the conditions of this jar, this drawing method, this counting procedure. If someone else does the same and gets different numbers, you investigate. Maybe the jar is different. Maybe the method is different. Maybe one of you made a mistake. Probability is public. It can be checked. The no smuggling rule. Now a very important rule. Gate 8 is the primitive ban. It applies to probability too. You cannot say it is just random. That is smuggling. That is treating probability as a primitive force. You cannot say the universe chooses. That is smuggling. That is treating probability as magic. You must always trace probability back to evidence, back to counts, back to calibration, back to repeatable observation. If you cannot, the claim is refused. The coin in the box example. Imagine a coin in a sealed box. You cannot see it. You do not know if it is heads or tails. What is the probability it is heads? Some people say 1/2. But why? Because there are two possibilities and we assume they are equally likely. But that is an assumption. It is not based on evidence. It is based on symmetry. In our world, that is allowed, but only if you declare it. Only if you say, under the assumption of symmetry, with no other evidence, we assign equal probability. And you must note that this is a weak measure. It could be overturned by any evidence. If later you open the box and see heads, the probability updates to 1. The branch set shrinks to 1, probability disappears. The weather forecast example. Imagine a weather forecast. It says 30% chance of rain. Where does that number come from? It comes from models, from past data, from many observations of similar conditions. The forecast has a calibration dossier. It says, on days like this, with these temperature, humidity, pressure, it rained 30% of the time in the past. That is a certified probability. It has scope. It applies today, here, under these conditions. If the forecast is wrong often, the calibration dossier gets updated. The probability measure may change. The predictions. Now we make predictions, not prophecies. Predictions like receipts, things we can check. Prediction 1. Probability only exists where branch sets have more than one member. If only one next step is possible, probability is 1 or 0, no in between. Prediction 2. Probability measures must come with calibration dossiers. If no evidence, no probability. Prediction 3. Probability measures are invariant under allowed transformations. If they change when we rename everything, they are illegal. Prediction 4. Probability measures have scope. They apply only within declared domains, families, and passports. Prediction 5. If two branches are equivalent within uncertainty, they get the same probability. No fake distinctions. These are simple. They can be tested, they can be audited. The failure signatures. Now we list the ways probability claims can fail. Each failure produces a refusal certificate that goes into the negative archive. Failure 1. No branch set. Someone assigns probability without listing the possible outcomes. Refused. Failure 2. No scope. Someone assigns probability without saying which transformer family, which domain, which passport. Refused. Failure 3. No calibration. Someone assigns probability without evidence. No counts, no observations, just a guess. Refused. Failure 4. Invariance failure. The probability changes under phi goes to phi plus c. Refused. Failure 5. Normalization failure. The probabilities do not add up to 1. Refused. Failure 6. Equivalence violation. Two equivalent branches get different probabilities. Refused. Failure 7. Primitive smuggling. Someone says it is random as if randomness were a force. No evidence. Refused. Failure 8. Scope creep. Someone applies a probability measure outside its declared domain. Refused. Failure 9. Outdated calibration. The evidence is old. Conditions have changed. The measure may no longer apply. Refused until recalibrated. Failure 10. Hidden assumption. The probability depends on something not declared, like observer choice or free will. Refused. The child who understands. Imagine a child listening to this story. The child says, "So, probability is just a way of saying what usually happens?" And we say, "Yes, based on what we have seen before." The child says, "Like if I drop a cookie, it usually breaks, but sometimes it doesn't?" And we say, "Yes, from watching many cookies drop, you can say most break, some don't. That is probability." The child says, "But if I catch the cookie before it hits the ground, then it doesn't break at all?" And we say, "Yes, that changes the branch set. New information, new probability." The child says, "So probability is not about magic. It's about what we know and what we've seen." And we say, "Yes, that is exactly it. Probability is a rule for distributing belief over possible branches based on evidence." The child thinks, "So, if I have no evidence, I cannot say anything about probability?" And we say, "You can guess, but you must say it is a guess. No calibration dossier, no certification." The child says, "And if two things look different but are really the same, they get the same probability?" And we say, "Yes, no fake distinctions. If they are equivalent within uncertainty, they are the same branch." The child says, "This is like being honest about what we don't know." And we say, "Yes, that is the best way to say it." The two paths at the end. Remember the two paths in the forest? Left path, right path? Your friend told you, left path is smooth, many people take it. Right path is rocky, almost no one takes it. That is probability. Based on evidence, based on counts, based on many observations. You do not know which path you will take, but you have a measure over the branches. Left path, high probability. Right path, low probability. That is all probability is. A certified assignment over possibilities, based on what we have seen. Not magic, not randomness, just evidence, counted and recorded. The measure registry. Now we have something new in our notebook, the measure registry. It lists every certified probability measure. For each, it records the branch set it applies to, the transformer family and scope, the calibration dossier, the invariance test results, the normalization certificate, the date of last update, links to the evidence. This registry is public. Anyone can check it. Anyone can challenge it with new evidence. If new evidence changes the measure, we update the registry. The main lesson. Let us say it one more time, in the simplest words we can find. Probability is a rule for distributing belief over possible branches based on evidence under a declared scope. No branch set, no probability. No scope, no measure. No evidence, no certification. That is it. Not magic, not randomness as a force, just counting, recording, and being honest about what we have seen. What probability is not? Now we say what probability is not. Probability is not a primitive force. Things are not random in some mystical sense. They are unknown to us. Probability is not a property of the world. It is a property of our knowledge about the world. Probability is not permanent. It changes as evidence accumulates. Probability is not universal. It applies only within its declared scope. Probability is not exact. It comes with uncertainty. The counts have error. The calibration has limits. The dice at the end. Remember the die? 6 sides, 6 possibilities. If we have no evidence, we might assume equal probability, but we must say it is an assumption. If we roll it many times and count, we get evidence. Maybe it comes up 1 more often, maybe 6 less often. Then we have a certified probability, based on counts, based on evidence, based on real observations. That is probability in our world, not magic, just counting. What comes next? Now we have probability. We have a way to talk about what is likely, based on evidence over possible branches. Next, we will ask, how do we update probability when we get new evidence? How do we combine probabilities from different sources? How do we handle situations where no probability measure is possible? Those are for later parts. For now, we rest here. We have probability as a typed measure over branches. Not primitive, not magic. Just evidence, counted and recorded. And we built it all from one simple idea. Probability is not a primitive. It is a certified assignment rule over the branch set, with normalization and invariance tests. That is part 18. That is what probability is. That is our story so far. Always. Peace be upon you.